So, ceiling jet thickness or the layer thickness. So, let us say when the steady flame height is much smaller than the ceiling height. Go back again. HF. This is H. HF is not here. I will go to the next slide. Here, I can say that HF, the steady flame height HF is much smaller than H. Then the resulting plume is called weak plume. So that's what I told. When you have a compartment, a small room, like in your hall or anything, if you have a small burner or even your domestic gas in a kitchen, it's a very small fire. That is going to cause some plume to come out, but it is weak plume because the flame height compared to the ceiling is much smaller. So that is weak plume. But if the HF is only less than H, not much less than H, then what happens? Then the plume becomes stronger and stronger. In some cases, HF can be say half of H. More and more the HF is more and more Q dot, more and more strength of the plume will be. As the plume strength increases, the ceiling jet also will be stronger. Okay. So let us first consider an example where a weak plume is there. Now the thickness of the ceiling jet at any radial location. So let us say this is diameter and this is the burning source. Okay, now a ceiling jet is formed. Now I say this is the line where the plume comes out, and this I call radius, for example. Okay, at any radius r, okay, at any radius r, what will be the thickness here, LT of the ceiling jet? At any location r, here, what is the thickness LT? That is correlated by Alpert. In fact, most of the ceiling jet correlations are proposed by Alpert. So LT, non-dimensionless with respect to the ceiling height, is given as 0.112 into 1 minus exponent of minus 2.24 R by H. So R is the radial location at which I find the thickness. Okay. Now locations of the maximum temperature and velocities, again they are dependent on the fire size. Okay. Now why we want this? Because we want to know the magnitude. When I design the locations of the fire safety devices, I need to see in a particular room there are some commodities which are kept at some locations. When some of the commodities is going to catch fire, we should know how the plume will propagate, how the plume will transfer as a ceiling jet, and how the ceiling jet will proceed towards these sensors. So, to understand the ceiling jet, Alpert has proposed several correlations based on systematic experiments and measured temperature, velocity, etc. for several cases where the heat release rate was varied from 600 kilowatts to about 100 megawatts, where the ceiling height H was also varied from 4.6 meter to 15.5 meters. So that is a thorough study from which some correlations are given. Please understand that there are some nomenclatures here. The ceiling height is H. Now that is this height Z is not useful for us, but from the source of the fire, the line of source of the fire, the ceiling jet spreads in the lateral direction. That lateral direction I call radius R. So now we will see quickly about the Alpert correlations. Okay, before going to that, we have to understand that this sealing jet can be steady or unsteady. Now we have some solutions given for weak plume as well as strong plumes. So we have to understand this. So basically, if there is steady or unsteady case, at a particular time instant, there will be heat release rate. Based upon that, we have to apply the correlations. Okay, so now you see that these correlations are characterized by the Q dot here, which is in kilowatt. So if the fire is steady, then Q dot will be constant. If the fire is not steady, then Q dot will vary with time. If Q dot varies with time, then I can find this, but it's very tough to really follow this. Basically, these correlations are proposed by constructing steady fires of different strengths or heat release rates and for various heights, that is the height of the ceiling. Now, T minus T infinity. T minus T infinity is given as 16.9 Q dot power 2 by 3 divided by H power 5 by 3. Please understand this empirical constant. And Q dot power 2 by 3 we have already seen, correct? That is the dependency of the heat release. The power 2 by 3 comes from the initial analysis what we have already shown. If it is a height factor, then 2 by 5 was used in the correlations, and for mass flow rate, heat release, etc., we can use 2 by 3 factor. Now, please understand that based upon the distance, this is the fire source, plume, and now jet, ceiling jet, this is the ceiling. So, based upon, so this is the r equal to, so r equal to 0 and r direction is this. So, based upon the radius, whether it is r by h or radius is less than or equal to 0.18 h. If radius is less than or equal to 0.18 h, I use this correlation. Why? Because the plume has just hit here, and this radius, first radius location here, it is in a region where the impingement also plays a role. This impingement also plays a role. But when you exceed this radius r equal to or is greater than 0.18 h, after that the plume influence will not come into play. Okay, so now we divide the location of the ceiling jet into two. One is the length from the r equal to 0 or the radius from the r equal to 0, where the influence of plume is felt. The second regime is after a radius where the influence of plume is not felt. So we cannot have one correlation. So that's what this means. That means in the first regime, the radius which is close to the impinging point of the plume, I get a correlation as 16.9 Q dot 2 by 3 power 2 by 3 divided by H power 5 by 3. Now, when you go to, that means there is no dependency of this with respect to radius. R does not influence this. Okay. Now, go to the region far off from the impinging point. That is, radius now is greater than 0.18 h. Please see the h can be, in this case, h is varied from, as seen in the previous slide, h is varied from 4.6 to 15.5 meters. So, when I say 0.18 into that means, so much meters I am away from the impinging point. Now, when you take the far off zone from the impinging point, now my correlation is T minus T infinity equal to 5.38 Q dot power 2 by 3 H divided by 5 power 5 by 3, but now the influence of radius is also given. R by H power 2 by 3 is in the denominator. When R increases further and further, what happens? The cool, there will be heat transfer from the ceiling jet and the temperature difference will drop. So that means from the impinging point till some radius r by h lesser than or equal to 0.18, there is no difference in the t minus t naught with the radius. There is no influence of radius. But in the far off point, you see that there is a influence of radius. As you go to higher and higher radius, the t minus t naught value will decrease. Because please see, h is constant, q dot is also constant. 5.8 of course is an empirical constant. So this far field or this near field, what we can say, that is the influence of plume is felt in this case where there is no effect of radius in variation. In the far field, the influence of plume is not felt. Similar in the velocity, the maximum velocity 0.96 into q dot by h power 1 by 3. That's it. When it's a slightly different value, r by h is less than or equal to 0.15 here. You can see here clearly that no influence of r as we saw in the t minus t naught, t infinity, basically because the plume is now coordinating the temperature and velocity distribution in this radius. When you go for higher radius, r is greater than 0.15 h, now you see that the radius is affecting. Okay, now this region where impinging occurs and the flow from this direction turns, this is called turning region. So turning region, the radius up to which this influence is there is r by h is less than or equal to 0.15 or 0.18, the turning region. Okay, that means the influence of plume is still seen in that region. So in these correlations, r and h are in meters, u is in meter per second and q dot is in kilowatt. Okay, now ceiling jet temperature and velocity near to the plume impinging point called the turning region does not depend on the radius. Outside this, it depends on the radius. So we have to understand this. So these are all correlated for steady fires, but we can extend this to transient fires. But you have to understand that in the transient fires, q dot is going to vary. When q dot varies, we have to understand how the temperature will vary with time, as q dot varies with time. Okay, Alpert correlations, when you have to apply them? After a given time period after ignition. So ignition has occurred, the fire should have reached some steady heat release condition. So when you ignite a fire, q dot versus time increases and becomes steady, then it may decrease. So now we cannot apply the correlation here in this portion, we cannot apply. After the fire has grown to some particular level where you have some average or constant value of q dot, then only we can apply this after time period after ignition. Now this will also allow us to see that some hot gases are accumulated in the ceiling and fire is not affected by the radiation from the walls. Do you understand? So Alpert correlation is generally applied after a time period after ignition when the hot gases accumulation in the ceiling is not high. So that means you cannot go to this point and apply this. So you have to take the value of q dot well before the hot gases accumulate in the ceiling or the radiation heat transfer is not going to be influenced. So take somewhere here, just after ignition, just after ignition, where the fire has grown to some steady level, you can apply the correlations. Now going to the near wall, so there is a chamber and fire now not in the center, it is occurring in the near wall or near corner. In this case, the correlations have to be modified. Okay, now how the modification is done? Again empirically, by observing what really happens when you move the fire source to corner or a side near to a side wall. General practice is to multiply the heat release by 2 for the near wall and heat release rate by 4. That is, if Q dot is the heat release rate for the central fire, then for the side wall fire you take 2 times Q dot. For the corner fire you take 4 times Q dot and apply the same correlation. That is what is some thumb rules are given like this. Okay. Now weak plume, that is HF is less than H. Heskested has given the heat release rate correlations basically in terms of total heat release rate. Okay, now Q dot, first of all he defines a term called Q dot subscript 0 star non-dimensional as Q dot divided by rho infinity Cp T infinity G power 0.5 H power 2.5. So you can see that this is the non-dimensional heat release rate. Now using this non-dimensional temperature difference delta T naught star is correlated like this for the weak plume. Okay, U naught star is correlated like this. Okay, where delta T is T minus T infinity. So you can see that the Alpert correlations are normally applied for somewhat stronger plumes. Now this is extended to the weak plumes like this by using this. So whatever delta T you get from the strong plume solution, you use this factor Q naught factor and get the distribution for the weak plume. So now see we have seen these two. First of all, the solution by Alpert's for this delta T and U, then some modification for the weak plume by Heskested. So now let us combine the Alpert's theory and the Heskested correlation to get the following expressions. So delta T naught star can be written as 0.225 plus 0.27 R by H per minus power minus 4 by 3 for this radius range, or in the turning region delta T star equal to constant 6.3. Again please understand that these are all for steady fires. Similarly U naught star is 1.06 R by H per minus 0.69 for the far region, and U naught star is constant for this. So when we combine these two we get this. So dependency of radius is present only in the far region, that is outside the turning region. Okay, so now what we have done here is Alpert correlation suggests that the solution for temperature and velocity depends upon whether we are seeing that in the turning region or in the far region. When you get the Heskested theory, we get some sort of normalization where you see that the delta T star is now written as delta T, which is got from Alpert correlation non-dimensionalized by T infinity divided by this non-dimensional heat release factor here, where the sealing height also is considered. Similarly, U star naught is U by root of GH. This is the characteristic velocity, and that is used to non-dimensional is U, and U from Alpert correlation can be used. Now, Alpert correlation shows that delta T and U are not going to be in the like for example in the turning region it doesn't depend on the radius, in the outside the turning region basically it depends. So by combining we can get these correlations. So the main thing is the non-dimensional temperature difference in the turning region is constant. Similarly, the non-dimensional velocity in the turning region is constant. Now strong plume solutions. When the height of the fire is comparable to the height of the ceiling, very very strong. See, so far what we have seen is solutions for something like this. Even here it's very very weak plume, it is somewhat weaker plume, not very weak. But now what we are trying to address is, if the flame height itself is comparable to the ceiling height, whether the heat release is very strong or the ceiling height is smaller, then we have to go to solution for strong plume region. Again, for steady fires, some correlations are available for this. Okay, correlation temperature for these cases has been reported by Heskested and Amada in 1993, where delta T by delta Tp, okay, is given as 1.92 R by B power minus 1 minus exponent of 1.61 into 1 minus R by B. Okay, what is B? B is the plume radius. Please understand now what happens. This is ceiling, there is a source. Now the flame itself, the flame height itself is comparable to the ceiling height H. So the plume does not even form, or forms and again immediately goes as ceiling jet. This is the problem now. In the previous case, like HF is much less than H or HF is less than H, we have a definite plume region. Then the plume impinges on the ceiling and ceiling jet forms. In the strong case, that is when I have a HF comparable to H, I have the solution dependent on the plume radius. Now you can see that so, the plume radius B also is in the correlation. So that is the radius, any radius from this, and the plume radius also now is taken into account. So R by B. Now one more thing is, what is Tp? The Tp here is nothing but the excess temperature of the plume. So for example, there is a plume temperature. So let us say plume just forms and ceiling comes. Okay. So that means here the HF is comparable to the H. So this temperature is Tp, and this is the, for example, this will be B, plume radius. So this temperature is Tp, that is the Tp minus T is the excess temperature at the plume axis at the ceiling, when it impinges on the ceiling. B is radius. You can use again the velocity based, so where the central line velocity decays, etc. So now we have to have some correlation for B, because it is not clear, because the ceiling jet and the plume again are very very close. Plume has formed very near to the ceiling jet, a formation of ceiling jet. So the correlation, first of all, for delta T depends on the Tp etc. here, and B itself is now correlated using this. So it's very very complicated. So strong plume, there is nothing called a defined plume or a separate ceiling jet here, or plume converting to ceiling jet. That particular sequence is not well defined. So you can see that the complicated, so introduction of B and expression of B again involving the plume temperature at the impingement point etc. are very very important in this. So these solutions, Alpert correlations for these solutions are well defined. So normally we can say that only when multiple commodities burn or the heat release rate of a particular commodity is very high, or the ceiling is very low, then only we will enter the strong plume regime, where these correlations or the interaction of the ceiling jet with the plume will be well defined, and we have to take into account of the uh, plume radius also in the correlation, and we need to correlate the plume radius with respect to the other factors. So, going back, these correlations, so as I told you, weak plume correlations, again when you have a correlation where HF is just less than H, but the Heskested has given some correlations in this way, non-dimensionalizing. Using these two, we have got these correlations, but these are all for steady weak plume fires. But when you go to strong plume, then what happens is the correlation becomes more and more complex. Okay, now how to use the correlations? Correlation for steady fires can be used in the case of slowly growing unsteady fires, as I told you before, correct? So, when there is a steady fire, all the correlations are valid because all the correlations are done by using a steady fire. Steady fire means the fire is sourced continuously and it burns for a longer time until which the measurements are taken. Then the ceiling height also is constant and so on. Now, when there is a growing fire, but if it is not very rapidly growing, it's only slowly growing, then we can measure the heat release rate as a function of time and use that in the correlations. So, at every time instant, you will get the value of delta T and U based upon the value of the heat release rate at the particular time instant. So, that is possible. So, use the steady state correlation itself in a transient manner. For that, these correlations are for unconfined ceiling jets. That means HF is less than H. So, that is obvious, correct. So, because we need a definite plume regime, and after the plume regime comes, we need the ceiling jet formation by that after the turning region and so on. So, in large storage facilities, we can very easily use this correlation without any problem. But in typical smaller compartment fires, these correlations cannot be modified, cannot be applied without modifications. So, large storage, the ceiling height is very high, so no problem. But when you go for smaller and smaller compartment, H reduces, and typically you go into HF comparable to H, then these cannot be used without modifications. Why? Especially in the unsteady fires. Why we are saying this? Because I have fire source and I have compartment, okay, a ceiling, and the fire plume forms and the ceiling goes. Now this fire is growing. So what happens? The hot gases go and the smoke layer which is hitting the ceiling will descend down. That is, LT will increase as the fire grows. And for example, if there is no ventilation, etc., this will descend down. The smoke layer will descend down. So, the smoke layer or the hot gas with the which is hitting the ceiling will descend down, okay, and will completely submerge the ceiling jet. So, that means that the correlation will not be valid. So, when these correlations are proposed, there are two things which were considered. One is the constant heat source, another one is the layer thickness was also taken as constant. That means, so provides some ventilation, this goes. So, after, so that means that there is a thickness, steadily the flow goes out, so that maintains the thickness at a particular level. So, that means when you don't have that particular or you have some unsteadiness in that way, then you have to modify this. Correlations for convective heat transfer from the plumes and the ceiling jets are reported in several, so that we can use convective heat transfer. You have to use. That means, see, for example, there is a, when it impinges, when plume impinges on the ceiling, or when the ceiling jet flows, there is a heat transfer to the wall. That's the wall, and the ceiling jet or the plume has some heat interaction with the wall. That can be also considered. Okay, basically we have several correlations for that, which we can use and improve your correlations for the ceiling jets. Then so far we have considered the ceiling to be planar, that is horizontal, but in some cases we can see that the ceilings may be slope. So some slope will be there. Now the proposed correlations can be basically have the some slope angle has to be included for this, for considering this. People have worked on that. So when you see the correlations developed for sloped ceilings, then the slope angle also will appear as one of the parameter. So you can see that the ceiling jet basically is a very important characteristics. The plume goes vertically upwards, hits the ceiling and develops as a ceiling jet, and the magnitude of temperature and velocity of the ceiling jet is very important for locating the fire safety devices. So these characteristics of the ceiling jet can be found from correlations which are developed by Alpert and Heskested. But only thing is these are for uh, plumes which are weaker. That is HF is less than H. But for stronger, there are some correlations. That is HF, if it is comparative to H, then there are some correlations, but which are very complicated. But all these cases are reported for the steady fires. When you have transient fires, then this correlation cannot be straight away used, especially when there is a accumulation of smoke near the ceiling, and that affects the characteristics of the ceiling jet itself. Okay.